Okay, sorry for the delay. So let's get started. So I'll just start with giving an overview or some of the basic ideas. So the toolbox is definitely not designed to solve all of your problems in MVPA. It's just designed to solve a set of common problems, and basically the 4 questions that are put there. That's what it's supposed to answer. So first of all, can we discriminate between multiple classes? And we've seen in Xiaojiang's talk and in my talk that a good way to estimate whether you can discriminate is cross-validation. So there's a cross-validation function. Sometimes your experiments have a time structure. So you have trials. This could be in functional MRI data or in EG data. So sometimes the question is, when can we discriminate? So at what point in time? Or the complementary question is, where can we discriminate? So this would be something like a searchlight analysis, where we actually want to see which of the features are discriminative. And another approach is actually looking at the duration of representations. And all of these questions I'll explain in a bit more detail in a moment. It's just some kind of design criteria. So that's the kind of the ideal I had. I don't know if it worked out, but the idea was to provide a high-level interface, so just for highly automated functions, but the implementation is quite low level. So I implemented the classifiers and even the optimization algorithms anew. And the idea is that it's easy to use and out of the box. So basically, first of all, you have all the example code, example data, which you should be able to run right away. And you don't need to compile any C code, and also you don't need any other specific MATLAB toolboxes, except for, I think, the statistics toolbox. And it should be non-invasive and pluggable. By this I mean that, first of all, it doesn't have its own data type, and the only thing it takes is a data matrix and class labels as input. So, and the reason is the way I like to work is, you all have your particular toolboxes you like to work with. So the idea is that you kind of plug in, if you want to use this toolbox, you just plug it in at some point in your analysis when you're working with, I don't know, EG-Lab, SPM, or FieldTrip, or whatever, and then you go back to your toolbox. And just a comparison to some other toolboxes. So there's a lot of MVPA toolboxes around, and if you work with one of them, you're happy with it, then by all means stick to it. I don't want to convince you to switch. But some of the differences are that many of those toolboxes provide wrappers either for MATLAB functions, and they're usually not very fast. And some other provide wrappers for libSVM and liblinear, which is, I would say, the industry standard for support vector machines and for logistic regression. It's a really, really great toolbox. The reason I opted not to do it is because it requires you to compile code, so it doesn't really work out of the box. And I think especially if you have never compiled code before, it can be a challenge. So I wanted something that works natively in MATLAB. And also there's some other toolboxes that use MATLAB, but they use the MATLAB optimization algorithms, which again are they're not as fast as the ones I use for the reason that they are very general purpose, so they cover lots of different cases, and the optimization algorithms I designed have special purpose just for the problem they solve. So for that reason, they can be faster. Okay, so I'll just explain the general interface, the way you interact with the toolbox. And if you've ever used FieldTrip, I actually borrowed the idea from FieldTrip. The way I set up the functions. There's 4 main functions, which I'll explain in a minute, and they are all used in the same way. So you call them on the command line or from your script with 3 parameters. The first CFG is just a MATLAB struct, and it contains a number of fields which specify what you want to do. For example, you can specify what kind of cross-validation you want, how many folds you want, and so on. The second input is your data, and there's 2 forms of data. Either it could be samples by features, so a simple 2D data matrix, or if your data has a time structure, it would be samples by features by time. And the third argument is simply the class labels. So, so far, the toolbox only supports binary classification. So the class labels would be 1s and 2s. And then basically each label in the label vector corresponds to one of the rows of your matrix. Okay? And so this is the basic workflow. So once you have your data prepared and your class labels prepared, you can use, well, there's two ways to work with the toolbox. One is to use one of these 4 high-level functions, and we'll check all of them in a minute. One is MV cross-validate, just implements cross-validation. The other one is called MV classify across time, where we use data with a time structure, and we perform a classification for each time point. There's a function called MV searchlight, which implements a searchlight analysis, which is also something that Shajang mentioned. And the fourth one is called classify time by time. In this case, the classifier is trained at each time point in a trial and tested at each other time point. So you basically get a 2-dimensional matrix of classification performance. And once you've done that, there's 2 functions to proceed with the data. One is called MV plot result. It's just giving you a visual representation of the results. And this is a function that's not ready yet. That's for the future. You would plug, the idea is that you plug in your classification result and you're able to perform some statistics. The other way to work with the toolbox, if you don't like these functions or they're not covering what you're interested in, you can just directly use the classifiers if you like them. And I'll show that towards the end, how that works. Okay. So let's look at the first example. So there's a cross-validation function, and we've talked about cross-validation before. So the goal is to get a realistic estimate of the performance. And to this end, the data is split into separate folds, and we train the classifier on all but one fold and test it on the whole dot one. And the result is then the classification performance, the cross-validated classification performance. So I'm now going to swap to MATLAB. And there is example 2. So I'm just quickly going to load the data and plot it just to show you what kind of data we're working with. So this is data from an EG experiment, but you could, in principle, use any other data. It could be structural MRI data or fMRI data. So just to quickly explain, so this is, the 2 colors here represent 2 different conditions. On the x-axis, we have the time, and this is an oddball experiment. And the red line is basically the ERP response to an oddball, and the blue lines is the ERP response to a standard stimulus. And the different lines are just different channels. I think there are 30 different channels. And what I'm going to do first is I'll just define an interval that I'm interested in. It's the interval from 600 to 800 milliseconds, so it corresponds to this interval. And I'm just averaging the data in this interval. So for the moment, we're not interested in the time structure. So I have this data matrix X. What's that? It's a matrix which is 313 times 30. So basically, in this experiment, I have 313 trials and 30 features, and the features are the channels, this time the EG channels. And let's look at the class labels. So the class labels are just 1s and 2s. So for each of the trials, it tells us whether it was an oddball or a standard stimulus. So the way it works, I'll just type it in, I think, so I can appreciate it more easily. So we set up the configuration struct, and in it we put some information. For example, let's say we want k-fold cross-validation. So we set cfg.cv to k-fold. Let's say we want 5 folds. And as I mentioned before, the separation of the data into folds is kind of random. So sometimes it's good to just repeat this process. So there's a parameter called repeat, and we're going to repeat it 4 times. And as a classifier, there's a field called classifier. We just use LDA, linear discriminant analysis, and we leave the rest as standard parameters. And so one more thing is metric. So we've talked about 2 performance metrics today. One is classification accuracy, and the other one is area under the curve, AUC. So you can use both. If you want accuracy, you would set the metric to ACC. If you want area under the curve, you would set it to AUC. So we'll stick with accuracy for now. And so basically, I call the function MV cross-validate. I input the configuration struct. That's my brain data. And that's the class label. And I hope it works. Yeah. So basically, there's a bit of output. If this output annoys you, there's a parameter feedback, which you can set to 0. Then it suppresses the output. It gives you some general information. So basically, what kind of cross-validation it's performing, the dimensions of your data, the class frequencies. So we have 32% oddball and 67% standard stimuli. And here it basically runs through the folds. So we have 4 repetitions, and we do 5 folds in each repetition. The classification accuracy we get here is 77%. Actually, let's run the whole line. So the first cross-validation was using LDA. The second one is using logistic regression. You see that's much slower. And the other thing I should have mentioned is, oops. So the function can give you a second output argument. So the first one would be just the classification accuracy. So it's just, in this case, 86%. The second argument is a structure which has some extra information. And you can basically put it into the plot result function. Result LDA. Discovered a bug. Okay. It just worked. Okay, I believe I did I don't know what I did wrong. Something went wrong. But basically, it doesn't do much. It doesn't give you high quality figures. It just gives you a visual representation of the classification results. Nothing more, nothing less. So I've basically run 2 cross-validations now. One was using LDA. The other one was using logistic regression. And it automatically always calculates the mean, which is not so interesting in this case. So the bars here represent the classification accuracy in both cases. OK. Before I move... Oh, yeah, sure.
So I noticed in your script, before you run the classifier, you Z-score the data. Is that considered good practice?
Yes, it depends on the classifier. So for LDA, it doesn't really matter. For logistic regression, it's good practice because it uses the exponential function. So if you have big values, you basically get numerical problems in your computer. So it's good to Z-score it. And for SVM, it's also good because both logistic regression and SVM use iterative algorithms, and they converge faster when you Z-score. So it's just a computational and numerical issue, actually. One last thing I wanted to show you here is I think Shajang made you already quite sensitive about overfitting, and the problem that we have in neuroscience is that we often have a limited amount of samples, but actually many features. And what I'm doing here is I'm reducing the amount of trials to 29, and mind you, we have 30 features, so we will have less samples than features. And what I'm going to do is compare cross-validation, k-fold cross-validation on this reduced data to running the function with no cross-validation, which would basically mean I'm training and testing on the same data set. And we're going to see how this affects classification performance. So I'm just going to run the whole cell, and we're just going to look at the output. So basically, this is the proper way. We do cross-validation, and we get a performance of 78%. We do the improper way. We don't use cross-validation. We train and test on the same data. We get 95%. And this is the overfitting. It's just overfitting to the noise in the data, and it wouldn't generalize well to a new situation. OK. Are there any questions at this stage? Otherwise, I'll move back to the slides. So we covered the first function. The second one is classification across time. So as I mentioned before, sometimes we have a time structure in the experiment, and we actually would like to have a classification result for each time point. Now you could just run a for loop and repeat the cross-validation function that we just used. And I basically wrap this into a separate function, which is doing it for you. And we're going to have a look. Oops, no. We're going to have a look into example 3. OK, this is very slow. OK, I've just run the analysis on using LDA. And you've seen that was quite fast, although it's actually a lot of analysis steps we do, because we have, I think, 131 time points times 5 folds times 2 repetitions. So that's one classifier was trained like 1,300 times. It goes very fast with LDA, and it's quite slow with logistic regression. So what am I going to do in the meantime? Maybe while it's busy calculating, I'm going to go back to the slides, and I'm going to discuss the next function, and we come back to the code in a minute. So basically, there's been a nice paper by King and Dehene in 2014, and there the idea was, so when we do this classification across time, it basically tells us at which time point we can discriminate information. But it doesn't tell us anything about how these time points are related. So for example, if we can successfully classify at 200 milliseconds and also at 300 milliseconds, you could ask a question, is the classifier learning the same information at 200 and 300 milliseconds, or is it different information? And if you interpret this information as something like representations, you can say like, okay, what's the duration of the representation? And this is what King and Dehene introduced with these kind of time-by-time plots. So basically the idea here is that you train the classifier, the training time is on the y-axis here, you train the classifier on each possible time point, but then you don't only validate it at the same time point, you also validate it at each other time point. So for example, you could train a classifier at 200 milliseconds and then validate it at 100 milliseconds, 200, 300, and so on. So you get a matrix of classification performance. And this tells you something about whether the information content across different time points is shared. So is the information at 200 milliseconds the same as the information at 300 milliseconds, or is it something else? So in their experiment, you can see 2 blobs here, which basically tells you there is a, the color coding here is AUC, so classification performance. This would basically tell you that there's 2 different types of representations. So if the classifier is trained in this time, it actually performs under chance level at the next, at 200 milliseconds, which is probably, I guess, it's probably an ERP flipping from positive to negative. But this would basically tell you that there's 2 different kinds of representations here. Okay, I'm sorry, I flick back because I think we are finished. Yes. Okay, so this is the result of the calculations I've just been doing. This is the mean. Okay, so we get two plots, and I've just run the code for LDA, that's the blue line here, and for logistic regression, that's the red line. Here the vertical line is the onset of the trial, so that's 0. And by the way, the shaded areas, that's the standard deviation across the different folds and across the different repetitions. So you also get a kind of idea about the variability of the estimate. One other striking thing is that apparently logistic regression can even decode pre-stimulus. And the reason is that it actually learns the class probabilities. So we've seen that one class has about 66% of the class trials are in one class. And logistic regression just picks it up. So whenever it doesn't know anything, it just says, okay, it's probably that class. And because it's 66%, you're right in 66% of the cases. And the second plot basically gives us a mean of the first two here. So that's not so interesting. So the other thing we can do is, and I'm just going to execute this cell as well. So what this does is there's 3 data sets with the same paradigm from 3 different subjects. And I'm just going to load them and run the MV classify cross time function 3 times, and then just going to plot the results. So this time, this is the classification result for 3 different subjects using linear discriminant analysis. The second plot that we see is just the mean. And this is the mean across the 3 subjects. And here the shaded area is actually this, I think, the standard error across the subjects. So this is like a grand average plot, basically. Okay? So let's go back to the slides. So we've talked about time generalization or time-by-time classification. So the purpose, you could say, is like tracking the time course of the representation. So how long do they actually take? Or how long does the brain stay in particular state? And as I just said, the idea is to train the classifier at a particular time point, T1, and then test it at each other time point, T2. And repeat this for all time points. So to show how this works, I'll go to example 4, classify time by time. And again, basically setting up the configuration struct is very similar. So again, we say our classifier should be LDA. For time-by-time analysis, it's good to normalize the data. So you could either do a demeaning or a z-scoring. I just do a demeaning here. As a classification metric, we want accuracy. And then we calculate the accuracy here. And then I just run it once again, and I set the classification metric to AUC. And then I run the code again. Okay, so I'll just execute the cell. So this takes a bit longer because it's training and testing at each combination of time points. Calculating performance. Almost done. Okay, let's look at the results. So this is the data for one subject. And on the left side, we see classification accuracy. So what does this mean here? Basically, the y-axis is the time the classifier was trained, starting from 200 milliseconds pre-stimulus to 1 second post-stimulus. And the x-axis is the time the classifier was tested. And the color coding is classification accuracy. It goes up to 0.8. basically you can see that we can't really decode in the first 200 milliseconds. And then there seems to be a blob from 200 to 400 milliseconds, and then a bigger blob ranging all the way up to 1 second. And the other plot is AUC. It's just to show you that in many cases the results look very similar. So it's qualitatively more or less the same here and there. So I just want to show you something else, is namely if we don't do the normalization, what the effect is on classification accuracy and AUC. Okay. Okay, so we see a problem here. So now we haven't done the normalization, and we see that when we take the classification accuracy measure, we get some decoding performance pre-stimulus, which is a bit weird. We don't get it with the AUC, so AUC looks pretty much the same as before. So in many cases, often enough, AUC is a more robust measure. It's robust towards, for example, changes in the threshold of the classifier. And this is actually the underlying problem here. Okay. The other thing you can do is you might have two data sets from, for example, one subject from two different conditions, and you want to see if the classifier generalizes from one data set to the other data set. For example, I don't know, if you have a, let's say, memory paradigm, does the classifier generalize from encoding to retrieval? In this case, I don't have different conditions, so I'm running it on different subjects. So basically what I'm doing here is training the classifier on one subject and evaluating it on the other subject. And this is the result. So basically, here the y-axis is the training time in subject 1, and x-axis is the training time in subject 2. And this is more or less the same, just the subjects are reversed. And what's shown here is basically training and testing on the same subject, but again, not using cross-validation. And actually, we get overfitting, and can somebody spot where we get overfitting and how you see that? The diagonal, yeah, very good. So we see even pre-stimulus, we can classify the diagonal, which shouldn't be the case. So again, always use cross-validation when you estimate performance. Okay, so we have 3 functions covered. There's one more to go. And this is the searchlight analysis that Shajang mentioned before. So basically here the idea is we want to identify how specific features or sets of features contribute to the performance. So this is about the where is the information. So basically what we do is we train and test the classifier using only one feature or a feature and its neighbors using cross-validation, and we repeat this for every feature. So in the end, what we get is classification performance for each feature. So we get a vector of classification performances. So let's look how this pans out. And this is example 5. And I load the same data set. It's the same ERP data set. And what I'll be looking at is so I'm ignoring the time dimension again here for simplicity. I'm just going to average in the 300 to 500 milliseconds window. And the first thing I need is you need to define, well, if you give a function just the features, it doesn't know which features are neighbors of others. So you need to define the neighborhood structure. In MRI space, this would be neighboring voxels. With electrodes, I'll basically calculate a matrix. Maybe I can just quickly plot it. MVPA-Light. So this is just a distance matrix. So each feature here, 30 features, is an electrode. And this basically gives me the distances between the electrodes in 2D, in the topography. And the MV searchlight function automatically looks for each electrode and its closest neighbors and picks those. So how do you call the function? It's pretty much similar. It has a few arguments that the other functions don't have. First of all is the neighbor matrix. And that's the matrix we have just seen that defines how close one feature is to the other features. You can also input a binary matrix. You don't need to have a distance matrix. A binary matrix where 1 means this is a neighbor and a 0 means this is not a neighbor. And average basically says that I want to so I'm giving it the trial with all the time indices between 300 and 500 milliseconds. So one option would be use each of these time indices for classification, or you just average them together to 1. And that's what the parameter average controls. The metric is what we've seen before. So we want area under the curve. And size just tells me what is the size of the neighborhood. So 3 says basically I classify each electrode and the 3 closest neighbors. So I have 4 features, basically. Okay, so let's run it. So here it tells me which feature it's using, which number, which neighbors belong to that feature. So for each classification, we use 4 features, right? An electrode and its 3 neighbors. So now we have a result for each electrode. So in EEG, we could just plot it as a topography. So that's what I'm doing here. So what does this mean? Basically, now the color represents classification accuracy. So this tells us where in the EEG the discriminative information is. So this is an oddball paradigm. So you would expect the central electrodes to be discriminative, and that's kind of what we find. So we find the highest accuracy around here. If you work with fMRI data, you could, of course, plot the result as a kind of map in MRI space. So what I'm doing next is I'm just going to vary the number of neighbors from 0. If it's 0, it just considers 1 electrode and none of its neighbors, to 5. And just run it multiple times. Okay, almost there. Is that one? So again, you can just call the function MV plot result. You give it the result. If you want a topography, you also need to give it the channels. And this contains the positions of the channels. Is there the figure? So basically, we did 6 analyses. So we varied the number of neighbors. So as a result, we get 6 plots. And so this is a plot for where each electrode is used on its own. Here we have 1 neighbor, 2 neighbors, 3 neighbors, 4 neighbors, 5 neighbors. And this is the average across those 6 plots, which doesn't make so much sense in this case, but anyways. Yeah. So I think we're done with that. We go back to the slides. So we've covered the 4 main functions in the toolbox. So I want to talk a little bit more. How much time do I have left, by the way, Mark?
Still enough. I mean, at least 15 minutes.
Okay. I want to talk a little bit about the classifiers that I implemented in the toolbox. So the first one is LDA, but it's not just ordinary LDA. So we've seen that many methods tend to overfit. And overfitting is more serious if you have few samples and a large dimensionality, which is very common in neuroscience data. And the kind of technical background is, so we've seen this morning in LDA, we're estimating the covariance matrix of the data. And if you have very few data and large dimensions, there's a bias. So the blue line here is basically the estimate from the data. And the yellow line is the true covariance matrix from which the data was generated. So if you have few samples, it's always too long and too slim, kind of. So what this shrinkage regularization approach, which is described in detail by the Blankets et al. 2011 paper, what it basically does is it blends the covariance matrix that we've found with a kind of spherical covariance matrix. And so it pushes it to be less elongated and less slim, basically, which is closer to the truth. And this has been shown to be very robust. And you can even run LDA if you have, so with this regularization approach, it even works if you have far less samples than dimensions. Okay, and so what I would like to show you is how you can train and test a classifier by hand. So this is something you would probably not usually do. If these 4 functions cover what you want to do, you would just use these functions. If you want to do something more fancy, you would maybe want to train the classifier yourself. So, by the way, at any point if I'm going too fast or anything is unclear, just interrupt me, please. So if you want to train a classifier by hand, first you run the function getClassifierParams. It gives you back the default classifier parameters. You can just look at them. This is the regularization term. So this is what we've just talked about. So this lambda basically tells you how much you blend. Maybe we should go over here. Yeah. So the lambda is a value between 0 and 1, and if you set it to 0, it basically is like ordinary LDA. It doesn't use the regularization. If you set it to 1, your covariance just becomes a circle, which is also not good. So usually you want a value in between. In many cases, it's not clear what the optimal value is. So there's 2 things you can do. One is you can set lambda to a range of values, and then the classifier will do another cross-validation within the cross-validation, an inner cross-validation, to find the best parameter. Or if you set it to auto, there's actually an analytic way to estimate the parameter, which usually works well. But this is something you usually don't need to think about. So the default is set to auto, and it's supposedly usually solves it automatically for you in a nice way. At least that's the purpose. So let's look what happens when we train a classifier. So for each classifier, there's a train and a test function. So this is called train LDA, and there's also a test LDA function, and the same for all the other functions. And the classifier is actually not much. It just consists of the classifier weights and a bias term. And this is actually the best lambda that it found. So the classifier automatically tries to estimate the best regularization parameter, and that's the one it found. And here we just apply the classifier to data. So we run test LDA. The first input argument is the classifier. And the second argument is the data. And here, for simplicity, I've not done it well because I'm using the same data for training and testing. And so the raw data you get out is the predicted labels, 1s and 2s, and the decision values, or the distances to the hyperplane. So again, it's something you usually don't need, but if you want them, that's always the second output argument. I think that's enough. So I'll just briefly mention the other classifiers that I implemented. Are there any questions so far? No? So the other one is logistic regression. With logistic regression, we have the same problem, that it tends to overfit, even more than LDA. And something I haven't mentioned before is a common approach to avoid overfitting is to push down the weights. So if you see if you look at classifiers that overfit to data, usually the classifier weights are extremely large. So a very simple way to avoid overfitting is just to force them to be small. And this is what the lambda parameter in logistic regression does. And so unlike LDA, the nice thing about LDA is that there's an analytic solution. So it's with a snap of a finger, you've seen it's really, really fast. Logistic regression doesn't have an analytic solution, and we have to solve it by iterations, which takes more time. This is why it's slower. So I've implemented a maximum likelihood estimate, and this is just a technical detail, using a trust region Newton approach, and this is basically the same approach that liblinear uses. So it's a state-of-the-art approach. And also here, usually you don't need to worry about the details because there's an automatic parameter selection as well. But in this case, it uses a search grid. And I'm going to talk about this a bit more. On the right side, this is just a visual impression of what the regularization what it actually does to the model. So on the top, you see if we have a very low amount of regularization, the model tries to adapt to the data very well, and it's quite able to do so. So it pushes one class gets all the probability 1, the other class gets the probability 0, and you see that it's a very sharp increase here. When you start to regularize more, you see that the slope gets a bit more smooth. So we increase the regularization here, and we increase it more here. But what you also see is if you look at the angle of this axis, it changes. It gets it gets more orthogonal, let's say, to the space. Basically, you can appreciate that in this case, if there's a few samples close to the border, they would strongly affect how it looks like, right? So this is, again, the overfitting. There's just a few samples that would strongly determine the shape of the classifier. Whereas if you increase the regularization, this is less of an issue. Okay. So the other second last classifier, support vector machines. It works in a very similar way. So again, the regularization is performed by penalizing the weights. And here the parameter is called C. Actually, let's have a look at param. No. So let's get the default parameters for SVM. So there's a C parameter, and again, the default is auto. So again, it tries to set it automatically, and in many cases, you don't need to worry about it, unless you want to. And it has a parameter for kernel. So if you want to use a nonlinear kernel, you have to change this parameter. Yeah, and the optimization procedure is also so again, we need a iterative optimization because there is no analytic solution, and this is using dual coordinate descent, which is exceptionally good in cases where you have small samples and a large feature space. So exactly the case which we often face in neuroscience data. It's very fast. I didn't do any benchmarking yet, but I tried a few things, and anecdotally, it's very similar to libSVM, which was quite astonishing for me because libSVM is compiled in C, whereas this is running in MATLAB. And so far, so you can, if the kernel is set to linear, you get an ordinary linear SVM. You can also use a polynomial or an RBF kernel. That's something I don't know if you remember it, we've seen this morning how they look like. And, whoops. So one other thing that's implemented is ensemble classifiers. And we've actually seen an example of an ensemble classifier this morning, which was the random forest. And an ensemble basically means that you train a lot of classifiers. In random forests, it's a lot of decision trees, but it could be arbitrary. You could train a lot of LDAs, for example, on subsets of the data. And so there's a function, there's an ensemble function, and it can use, so in ensemble learning, the kind of small classifiers that you train are called learners. And basically, if you use ensembles, you can use any other classifier in the toolbox as a learner. So you could use LDA or logistic regression or support vector machines. But mind you, it of course, since you train lots of classifiers at the same time, it's quite a computationally expensive process. 5 minutes? Okay. And also, so I've said the industry standards are liblinear and libSVM. And liblinear implements logistic regression linear SVM, and at least anecdotally, I think it's faster than my MATLAB implementation. So if you like these two packages, there's also an interface in the toolbox. So you can call if liblinear or libSVM is in your path and it's compiled, you can set a classifier to liblinear or libSVM, and it will just use that code for all the functions that you've seen so far. Okay, so I'll just want to mention a few more technical details. So kind of remove the lid a bit and just mention a few things that I put in to speed up the processing. So one concept is the regularization path. This is basically the concept is about how do the classifier weights change when we change the regularization parameter. And what this plot shows is the change of the classifier weights for logistic regression as you increase the lambda parameter. So each line here is one feature or one channel, one EG channel. This is on the data that we've just played around with. And so basically what you see is as we increase the lambda parameter, eventually all the weights get pushed to 0, which is exactly what I said before, which is a good way to counteract overfitting. So the problem is, if you want to estimate the best lambda, actually you have to test the classifier many times, train and test it, trying out different lambdas. For logistic regression and SVM, there's no way to calculate the best lambda. You can just test it. And what this shows is basically, on the left side, is the number of iterations of the algorithm, of the optimization algorithm, as you increase the lambda. On the right side is the same situation, and it's using a kind of a prediction model that I implemented, which basically, I think I can show this best in this. So what the line and the circles here denote is for two features the weights we get as we increase lambda. So we start a small value of lambda. As we increase that is the path that the coefficients take, and the pluses are actually the predictions I implemented. And the way it works is once you've calculated, let's say, these three values, it fits a polynomial model and tries to predict the next value. And you see, in many cases, it's pretty close. And sometimes it nails it exactly. And the only effect of this is that you speed up the computation. So the optimization procedure converges much more quickly. And this is actually what's shown in this plot. So on the right side, we see the optimization when you use the predictive model. And you see that in this range, we need like 8 or 9 or 10 iterations in each turn. And this is pushed down. Well, in this range, it's pushed down to 0. So the prediction is 100% or like up to tolerance accurate. And we don't need any more optimization. And it's seriously pushed down for the other values. So this is like one trick to speed up the classification. Why is that speed so important? Well, in many cases, we actually have to train a classifier a large amount of times. So if you imagine we have 600 time points, 5 folds, 5 repetitions, we have to train a classifier 15,000 times per subject. If you also tune the hyperparameter, so you also do additionally a 5-fold cross-validation in the training procedure, it's 75,000 times. And I actually missed here that usually it tests out, let's say, 10 parameter values. So it would be times 10. 1 minute. OK, I'm almost done. It would be 750,000 times. So even saving a fraction of a millisecond can make a big difference for the computation time. And this is just quickly mentioning some other things that I've implemented to speed up computations. One is that if you use kernel SVM, the kernel is pre-computed, which is not done by libsvm and liblinear because they're also meant to work with large data sets, 10,000 samples, 1 million samples. There it's not feasible to do it. For small data sets, let's say up to 1,000, 2,000 samples, it's feasible and it speeds up things. And this is just mentioning some things that are not yet in the toolbox, but I want to include eventually. One is multi-class classification. So far, I've implemented only binary classification. I haven't implemented the stats yet. Eventually, I would probably add some kernels that might be interesting for neuroscience data, such as a dynamic time warping kernel or a Riemann kernel for covariance classification. And I think for the sake of time, I'll skip the other details. So thank you for your attention. Any more questions? Yeah?
Yeah, really nice, by the way. But I was just wondering if there's any way to do this, or when you've got circular features. So, phase, for example.
Okay.
Is there an implementation that can deal with that?
Well, I know what people usually do in this case is they take, I think, they map it to the two-dimensional space, because if you have a circular feature, it's on a circle, right? So you map it onto the cosine and the sine, so get two features out of it, and then you can use linear classifiers or anything else. So I think that, I have never worked with circular features, but I think that's what people usually do. Yeah?
I have a question. In logistic regression, if we have those logistic functions, how tell to interpret their slopes? Because I can have different slopes, but is it like a center of the slope of a line which discriminates between classes, or what's the purpose of adjusting the slope? Why don't you just make it, say, vertical?
Well, if the slope is very sharp, you get this overfitting problem, because then samples very close to the, so to say, the hyperplane, they will affect the classifier a lot. If you make it more shallow, then the violations of the classifier don't count so much, because it's a much more smooth, it's much more smooth change. In many cases, you don't really use this slope or these probabilities. What you can do, and you can also do in the toolbox, is the classifier can output probabilities. And that would be actually the values along this slope. So you can get a probability for each sample if you want that. And that's what people sometimes want. But in many cases, you wouldn't be interested in that. But, yeah. OK.
Well, so thank you, Matthias, for a brilliant talk. And now it's time for lunch. And see you, well, first of all,